All right, this is part 2 of quantum mechanics, chapter 8 in the new Tro textbook, 5th edition. And just continuing along with the idea of Max Planck had developed a new theory in the year 1900. Actually, it was a little bit before that. He won the Nobel Prize in the year 1900 for his work on quantum mechanics. It turned out to be able to describe and to solve mathematical problems that were unsolvable up until that point, and it gave the correct description of the electron and the atom. So there were problems in classical physics and chemistry that led to the development of the field of quantum mechanics, and Planck is considered to be the father of quantum mechanics. Next slide here. First line says Max Planck again. He proposed that matter has quantized energy levels. Right at the same time, Albert Einstein talked about matter which absorbs and emits light, and it was in multiples of energy units. So if matter has quantized energy levels, then light can come in and excite an electron in a lower state and promote it up to another state. The energy of the photon is the word we used for the particle of energy. If the energy of the photon matches the energy difference of the energy levels of the electron, then absorption will take place. So also in this slide, this is a picture from your book. So just to give you a little bit more insight into what the quantized system is, here's the guy who's climbing up this slope here, and he could just take step to get up to the top. The idea of quantum mechanics is that, you can take steps instead. You can get to the same place, but in steps. And I mentioned this in the last video, that there's no such thing as a half step or a third of a step. It's either this step or this step or this step, and that's the way it is with absorption of energy by matter. Okay, now there is an equation that I also showed you last time, that the energy associated with these steps is equal to the frequency, Planck's constant h times the frequency of the light, and then the frequency is equal to the speed of light divided by the wavelength. So depending on what you want to do, if you have frequency and you want to calculate the energy, calculate the frequency of the light, or maybe you have wavelength and you want to calculate energy or frequency, you can go around and around with these equations and calculate everything. So you've got these same constants that I showed you in the last video. C is equal, this is this equation for the speed of light c, which has this numerical value. It's equal to the product of the wavelength and the frequency. And so one is reciprocal of the other. And so when absorption or emission occurs, there's an exact match in the frequency of light and in the energy level differences in the atom or molecule. This is another slide that says the same thing. Photons, or these energy particles, can be absorbed or emitted by matter if the photon energy matches the change in energy. Delta E is equal to h nu. So on the left-hand side, first of all, in the diagram, you can see that these lines are equally spaced, meaning that the energies of the different levels. Also, I should have noted here, this is E1, E2, E3, E4, like that. So the energy difference between E4 and E3 is equal to, so if energy is equal to h nu, it's actually, there's an n in the equation as well. So E is equal to the quantum number times Planck's constant times the frequency. So if it's at the fourth, if n equals 4 here, then the energy is 4 times h nu. If n equals 3, the third level, then energy is 3 h nu. So you take the difference between them. So that would be the difference in energy between the levels. So E4 minus E3 is 4H nu minus 3H nu, which is equal to H nu. Same thing if you took E3 minus E2, you're going to get H nu again. E2 minus E1, you're going to get H nu again. So that's where that E equals H nu equation comes from. But each energy level has an N there associated with the quantum number N. Okay. Now, we'll digress for a moment here. Now, the issue that matter behaves like a wave, that was like that fourth point that I was making in the last video. In this case, of course, we're interested in the electron, which behaves like a wave. But de Broglie, this was around 1926, came up with an equation. He was a very young guy. He was actually working on his PhD thesis in, I believe, Belgium. And he ended up deriving this equation. It took him about a page of notes. I think his PhD thesis is 2 pages long. And he ended up winning the Nobel Prize for this work, which is pretty funny. Anyway, this is different than the equations that I've showed you before. And usually I derive this equation for my Chem 101 students or 151 students, but because we're short on time, I just decided to give it to you. Okay, so if a particle is in motion, it has a mass and it has a speed or velocity. And this is a, whenever you have anything quantum mechanical, Planck's constant keeps coming up, this number here. Anyway, so you have the particle in motion. So I'm walking, across the street. I'm walking, and is there a wavelength that's associated with me doing that? My mass and my speed, the product of those two is inversely proportional to that wavelength. So if this product here is large, this wavelength here is going to be really small. But is there a wavelength? Do I have wave-like properties? Or if you throw a ball, does the ball have wave-like properties? So here's some examples. Start with the golf ball. The mass is 10 to the minus 2 kilograms. The velocity might be going at 30 meters per second. And if you use de Broglie's equation, you're going to end up with a wavelength that is 10 to the minus 25 nanometers. This is so extremely small that you would never ever be able to detect that. All right, now snail, similarly, 10 to the minus 2 kilograms, 0.001 meters per second. You get 10 to the minus 20 nanometers for the wavelength associated with the snail in motion. You can't say that there's no wavelength. It's just a wavelength that's very, very small. But on the other hand, with an electron with a really small mass, this is in kilograms, 10 to the minus 31 kilograms, it's possible to do experiments where you can accelerate electron in the presence of a magnetic field or an electric field, and you can get it up to 10 to the 5th meters per second easily. So you put it into the de Broglie equation and you end up with a wavelength of 1 nanometer. And the question is it possible to detect 1 nanometer? And the answer is yes, it is possible. And the wave length and the wave properties of the electron are utilized in the scanning electron microscope. And it is it's incredible because it's the interference of the electron waves that's used in that microscope. So I was talking about that in the last video, the interference properties of the wave. So yeah, electrons do have wave-like properties that are significant, and we can extend that to the idea that the electron has standing wave properties. They're orbitals, and the orbitals are going to be associated with waves and wavelengths. All right, here's just a picture. I drew a couple of these orbitals in the last video, but here's a little bit more systematic picture of some of these orbitals. And it's nice because you get the 3D picture here. So you have s orbitals, and here you have 3 p orbitals. One's called px. That means it's oriented along the x-axis. Pz is on the z-axis, and py is on the y-axis. Then there are 5 d orbitals, dx squared minus y squared, dzx, d3z squared minus r squared. This is a little different than the way I usually present this. dxy, that's normal, that's normal. This one, that one. Yeah, this is the only one that's different. Sometimes it's just called the dz squared. So it's just that part of it right there. But they all look pretty different. You got 1, 2, 3, 4 of them that have the 4 lobes. And also, by the way, I mentioned it last time, there are nodes as well, right? Wherever there's 0 amplitude motion in this standing wave pattern, those are nodes. So the p orbitals have 1 node. In this case, the d orbitals have 2 nodes. Anyway, so the ones, the xy, the yx, and the dx, those are, if you drew an xy plane, they would be, the lobes are kind of in between the axes. This one, it looks similar, except that it actually lies on the xy axes, and this one looks completely different. This is like a p orbital sitting in a donut. And the f orbitals are even more complicated down there, and I'm not going to ask you about those. So just they're very pretty to look at, though. All right, so the quantum numbers we saw in the guitar string, n is 1, 2, 3, 4, etc. But in the case of the electron wave, there's an equation called the Schrodinger wave equation, and it's pretty complicated calculus. It takes a long, long time to actually solve it by hand, to actually write it all out. I've taught this class before, and it really takes weeks and weeks to get through all the background material before you can even solve for it. But anyway, it's good to know that there is such a thing as a Schrodinger wave equation. It's used to solve for the orbitals, so that's like their wave behavior, what they look like, and their energies. And it's like the guitar string problem, except that it's for a 3-dimensional spherical problem and blah blah, pretty detailed stuff. But anyway, when you actually want to solve the equation, you have to introduce quantum numbers. And it turns out there are 4 of them that are needed to solve the equation for the orbitals. And so those 4 quantum numbers are represented by the symbols N, L, M sub L or subscript L, and M sub S. This is the one associated with the main energy levels. Then there are some sub-levels, sub-sub-levels, and then this one has to do with spin. So we'll look at each one of those. All right, the first one is the n equals the n principal quantum number. It's just like the guitar string. N is equal to 1, 2, 3, 4, etc. It indicates the main energy levels. Sometimes we call them shells as well, but I'll stick to the word levels here. And it's interesting because if you look in the periodic table, this is the next chapter, you can see that the first row in the periodic table is associated with this number, second row, third row. I'll show you that. And also, the larger the value of n, the greater the energy of the electron is. And also, same idea as the guitar string, the number of nodes in the orbital is n minus 1. So if n equals 3, then there's going to be 2 nodes for the orbitals in that set. All right, the second quantum number is L. This is subscript L here. In some of my older notes, when I typed L, it just looks like a 1. So watch for that in the group activity. I think I probably have fixed it by now. But azimuthal quantum number. Azimuth has to do with the angle that the orbital would be in relative to the axis. Don't worry about that at all. But anyway, so if you have a certain value of n, then L, the second quantum number, can go all the way up to n minus 1. So if you have the quantum number 3, for example, L can be 0, 1, or 2. Okay. And then these numbers 0, 1, 2, 3 correspond to, and I have it in a table here, the L quantum number. If it's 0, that is associated with this subshell that's called S. So in other words, there's two ways to say the same thing. One is that the quantum number L is 0. The other is to say we're talking about the S subshell. So L equals 1, that's associated with the same thing as the P subshell. L equals 2, same thing as the D subshell. 3 is the F subshell. And then the orbitals are within each one of these subshells. All right, that and also the azimuthal quantum number gives you information about the shape of the orbitals and the nodes and all that. All right, the third one is called the magnetic quantum number, and this one is M. And again, in my old notes, it looked like a 1 there, but I changed it for the most part to a script L. Which is what it's supposed to be. So you take the value of L, the second quantum number, and you put it here, and then you take the negative of it and you put it here. Let's say, for example, it's let's say M sub L is equal to 3. Then you'd say 3, negative 3, and then you want to take, you want to take integer values in between. So L equals 3, there's 1, 2, 3, 4, 5, 6, 7 possible numbers for the magnetic quantum number. And these are associated with what I call sub levels. You'll see reference to that in some books. And the sub levels are observed in the atomic emission spectrum when the atom is in the presence of a magnetic field. All right. So these electrons, when they're moving, they have magnetic properties. If you put the electrons in the presence of a magnetic field, the spinning electrons or the revolving electrons, depending on what the type of motion is we're talking about, there's always like a magnetic field associated with any kind of circular motion of a charged electron. And so that magnetic field aligns itself with or against the external magnetic field, which is what this would be. And it just causes slightly different energy. So the one that's in alignment with the magnetic field is lower in energy. The one that's opposite, not aligned with it, will have a higher energy. Just trying to give you a feel for some of this stuff. All right, and then this corresponds to orbitals. So the orbitals then have different energies when they're in the magnetic field. So without the magnetic field, we can say that all 3 p orbitals have the same energy. In the presence of the magnetic field, they don't. They're slightly different, and it has to do with the fact that they're oriented around their axes and the magnetic field. All right, you don't need a picture of that, don't worry about that, but just some comments there. I'm trying to get you to be able to work with the numbers and get all the way down to the orbitals and predict which one's there. All right, so summary of what we've done so far. You can talk about an L subshell, P subshell, D, and F. So when L equals 0, it's an S subshell. When L equals 1, it's a P, like that. And then next is the M sub L. If L equals 0, then M sub L is equal to 0. If L is 1, then you have 1, negative 1, and integer values in between. Similarly, with 2, you have 5. And remember, M sub L, that third quantum number is the one. These are the orbitals. L is the subshell. M sub L is the orbitals. So there's 1 orbital in the S subshell. There are 3 p orbitals in the P subshell. There are 5 orbitals in the D shell, and 7, which one I just wrote down. There's 7 in the F shell when L is equal to 3. So that's what is said here in this next row. 1 s orbital, 3 p orbitals, 5 s orbitals, and 7 f orbitals. Those are good numbers to know. And then in just a second, I'll tell you about the spin. When you introduce the spin quantum number, that fourth one, you'll see that for every orbital, it can actually fit. That's not really quite a good description, but we use it all the time. This one can fit 2 electrons. You have 3 p, so there's 2 electrons for every orbital. So if you've got 3 orbitals, there's a total of 6 electrons. If there's 5 orbitals, there's 10 electrons. If there's 7 orbitals, there's 14 electrons. All right, and so the spin, not here. These are just more pictures of the orbitals. These are nice pictures, actually. So you have the s orbital, the p orbitals, and you can see that they're oriented along the axes. And then also the d orbitals, you can see the orientation. So you have for the YZ, you have the YZ axes, and then the lobes are in between. That's what I was describing earlier. For this one, they're on the axes. And for 1, 2, 3, they're off the axes. And this is the DZ squared, which is oriented along the z-axis right there. I would like to show you some other orbitals. When you get to higher values of n, you can see these really beautiful circular nodes and stuff, but I'm going to pass on that for this semester since we are very much trying to move along. We've got more chapters to cover after this. So you can ask me about that though. Here's another depiction of these same orbitals that I was just showing you. And this is kind of organized in a table. So if n equals 1, then remember L can go up to n minus 1, so L can only be 0. And if L is 0, then you have M sub L being equal to 0 as well. If n equals 2, it can be either L equals 0 or L equals 1, because L goes up to n minus 1, which is 2, right? So it can go 0 or 1. If it's 0, then it can only have one orbital. If it's 1, then the third M sub L quantum number is plus 1, 0, and minus 1. So there's 3 p orbitals. When n equals 3, you got an s, 3 p's, and 5 d's. So it's probably, oh, let's see if I should do that right now. Yeah, let me see if I can do that before we go on. Slide again. All right, so if n equals 1, there's only 1. That's the 1s. If n equals 2, you have 2s and 2p, which is what I just did. If n equals 3, you can have 3s, 3p, and 3d. And then if n equals 4, you can also have the f orbitals as well. We're not going to talk about the f's. Okay, so then the three-dimensional spherical wave patterns called the orbitals have the names in this order: 1s, 2s, 2p. All right, let me do it again. 1s, and then when n equals 2, you have 2s, 2p. When n equals 3, there's 3s, 3p, 3d. When n equals 4, you have 4s, 4p, 4d, 4f. So, for example, if you have the principal quantum number being n equals 3, then L, the second quantum number, the azimuthal quantum number, can be 0, 1, or 2. So 0 or 1 or 2. If it's 0, then M sub L can only be 0. If it's 1, then M sub L can be 1, 0, minus 1. If L is 2, then M sub L can be 2, 1, 0, negative 1, and negative 2. I showed you in tables, but sometimes it's just good to start with nothing and write it out. All right, so then the orbitals are this third quantum number. So this is an s orbital. In fact, it's a 3s orbital, okay, the 3 here. Here you have 3px, 3py, and 3pz. Then here you have 3dxy, 3dxz, 3dyz, 3dx squared minus y squared, and 3dz squared. So there's 5 orbitals associated with 5 m sub L quantum numbers. Okay, and then if you had n equals 2, you can look at this. I always start with 3 because you can see so much with that one. If n equals 2, then L can be either 0 or 1 because it can only go up to n minus 1. 2 minus 1 is 1. So then m sub L will be 0 for this one. For L equals 1, m sub L will be 1, 0, or minus 1. So this corresponds to a 2s orbital, and this would be a 2px, 2py, that's a y there, and 2pz, like that. All right, and then you can picture those on different axes and whatnot. If n equals 1, L is equal to 0, m sub L is 0, and the only one that corresponds to is a 1s orbital. So that's how you generate the orbitals from the quantum numbers. So it's useful for me to sketch it. Now there's one more quantum number. It's called the spin, and you know, in quantum mechanics, it's just a very, very different situation. You talk about the probability of finding the electron in the atom and things like that. It's very different than the idea that the electron goes around in an orbit. We're talking about orbitals instead of orbits. But I mean, if you think about the sun, and then the planets are going around the sun, and then at the same time the planet spins on its own axis, that is similar in many ways. That's a classical picture that I just drew you, but there's similarities. So the spin quantum number, I mean, now you really got to think about it classically, although it's not at all. But you can talk about the fact that the electron spins on its own axis, right? It either goes what's that one? That one's counterclockwise and this one's clockwise. So one of them, and this is in the presence of the magnetic field as well. Or let me start over again. The spin is intrinsic, but when it's in the presence of the magnetic field, the energy of one of them is a little bit lower than the energy of the other, because remember, every time it spins, there's this magnetic moment. Whenever you have a spinning charge, there's a magnetic moment, and the magnetic moment aligns itself with the external magnetic field, either with it or opposed to it. So that's why the energies are different. So think about it that way. In terms of the energy, basically you take 1/2 here and multiply it times h nu. That gives you the energy. Don't worry about that. But we use plus 1/2 and minus 1/2 as kind of an abbreviated symbolism. It doesn't matter which is which. You can say this one's means that the spin is with the magnetic field. This one means it's against. Whatever. That part doesn't matter. Anyway, there's 2 possible spins for every electron. So then the Pauli exclusion principle here shows you that you can have an so okay, let's read what it says. No 2 electrons in an atom can have the same set of 4 quantum numbers. Each electron in an atom will have its own unique set of 4 quantum numbers. So here's an example where 2 electrons, and this is the point here, that 2 electrons can exist simultaneously in the orbitals. And we just pick in the 2p. Excuse me. So you have n equals 2, and then L is going to be 1 if it's a p subshell. M sub L is minus 1, so that's one of the 3 p's. Px, py, pz. It doesn't matter which one it is. And then we'll call it x, but it could be y or z. It doesn't. The negative 1 doesn't really mean one or the other. So The first three quantum numbers for the first electron are n equals 2, L equals 1, m sub L equals minus 1. And if you want to give it the fourth quantum number, you can say, okay, m sub s is equal to a half. So there's another electron, because Pauli exclusion principle says each electron has its own unique fourth set of 4 quantum numbers, or no 2 electrons in an atom can have the same set of 4. So you could have another electron, which is a 2px, but it's spinning in the opposite direction. So that's why, and I'm sure you've seen this, you have this line to indicate the energy of a particular orbital, and then you use the notation spin up and spin down. So 2 electrons can fit into 1 orbital. Okay, so if that's the case, then the 1s can fit 2 electrons, the 2s can have 2. Since there's px, py, pz, each one can have 2. There's a total of 6 now for 2p. 3s can have 2. 3p can have 6. For the d's, there's 5 orbitals, and each orbital can have 2 electrons. One would spin up and one would spin down, so there's a total of 10. 2, 6, and 10 again. And then you have the 14 for the f orbitals. Don't worry about that. All right, but anyway, you see that there's some repeating here. You get this set, and then you just substitute 3 there. You get one more. You substitute this set here, and then you get one, like that. Okay, now this diagram is in 2 parts. So in the absence of the magnetic field, you have a situation here where the 1s comes first, that's the lowest energy, then you have 2s, 2p, xyz, 3s, 3px, 3py, 3pz, then you have 3d, so 3d xy, 3d xe, and so on. 4s keeps going up like that, keeps going up. So in the absence of the magnetic field, you would say the configuration, that's the word here, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 310, 3d10, 4s2, 4p6, and so on. It's just in order, okay? But in the presence of the magnetic field, things change. So the external magnetic field affects orbitals, electrons as orbitals that are pointing in different directions. And some of them are more affected by the field than the other, just because of their orientation, their shape, which axes they're on, and so on. So it changes, and this is the one you're familiar with, I'm sure. So the 1s is lowest, then the 2s, and we did it here too. No, we didn't. So the 3p's are just kind of they start in the same place. But anyway, you take the p's and you push them over to the right. So 1s, 2s, 2p, just look at the order here. 3s, 3p, then you get 4s, and what's strange here, in the figure above, this 3d is down lower, right? 3s, 3p, 3d, and then 4s. But here, the 4s is lower than the 3ds. So it's different. And then you get 4p, 5s, 4d, and 5p. So that's the one you want to worry about, because you don't think about electrons being in the presence of a magnetic field, but again, anytime the negatively charged electron is moving around in that atom, it has a magnetic field that's perpendicular to that circular motion of the charge. And so if there's more than one electron in the atom, the magnetic fields perturb each other, and you get this, the second situation. So in the presence of the magnetic field, which can be external, you can have it, put it in, get a magnet and see the effect. Or this is for a many electron system where the magnetic fields are perturbing each other. Now up here, in the absence of the magnetic field, if you don't have an external field, this diagram works for one electron. Fine, that would be the configuration if it's just one electron. But in the lower situation, you got many electrons where they're perturbing each other and changing the energy levels. And also the other point is that there's always this convergence between quantum mechanics and classical mechanics. And so this original diagram actually correlates with the Bohr model. And so if you have the nucleus and the electron going around in a circle or an orbit, and then you get the next one and the next one moving. I'm just making it go counterclockwise for no reason. But anyway, the electrons are going around at different levels. And so you can number them. N equals 1, N equals 2, N equals 3, N equals 4, like that. And that correlates with the energy diagram that you saw for hydrogen. So you have to go back and look at it. But you've got, actually, I take that back. Yeah, there's another way to draw this. So if you had 2s and the 2p, so everything to do with 2 is all in a line, then it would correlate perfectly with this diagram. But actually, I'll just skip that point because I'd have to redraw the whole thing, and I don't want to do that. So we'll just move ahead and say that there is a relationship to the classical theory, which is always the case. With quantum mechanics, you get all this detail, but you look at kind of the bigger aspects of it, and it correlates exactly with the way classical physics had first interpreted some of these unusual effects in the spectra, electronic spectra. All right, this is my last this is my last one, and I actually did this table myself. I spent quite a bit of time last semester doing this. And you can look at this thing. You don't have to go crazy over it, but for example, if n equals 3, you have the possibility of L being 0, 1, or 2, right? And the name of the subshell is SPD subshells. The possible values of the M sub L. So if L equals 1, M sub L is 1, 0, negative 1. L equals 2, 2, 1, 0, negative 1, and 2. The names of the orbitals associated with the 0 is 3s. Then you have px, py, pz for 1, 0, negative 1, and so on. And then you can count the number of orbitals in the subshell. So if you've got 5 orbitals here, you enter 5 here, 3 and 1, and so on. The spins can be up or down, or plus or minus a half. So if you've got 1 orbital, you can have 2 electrons. The maximum number is 2 that can fit into that orbital. If you've got 3 orbitals, there's a maximum number of 6, 5, maximum number of 10. And then you can add up maximum number of electrons in the main shell. And so the main shell, n equals 1, there's 2. For n equals 2, there's a total of 8. 2 plus 6 is 8. Here you've got 18, and here you got 32. And these are these magic numbers. Even if you draw the circles, the orbits, you can fit 2 in the first shell, 8 in the second, 18 in the third. And when you start to talk about Lewis dots, these are the numbers that are relevant. But there's a little formula here, 2n squared. So if you have n equals 3, square it, that's 9 times 2 is 18. So it's just a way you could calculate that. Anyway, okay, hang tight. The next chapter starts with the electron configuration. We're going to relate it to the periodic table. There's a lot more insight that you'll have when we start looking at the periodic table. And then we'll start to talk about Lewis dots. Thank you.